Já está aí.
Já testei. Como é que passa ao slide? Passa aos slides.
Tem que lá.
Mas lá dentro é preciso ligar ao computador, não é?
Os slides não estão a passar.
Não estão a passar?
Não.
Ah,
ok. So, Luís, vamos fazer em inglês, que é para a nossa. Okay. So, for those of you that weren't here before in the other sessions, welcome, and welcome again if you were before. So this is the last keynote of the event, presented by Luís Pessoa, area leader of the optical communications technology. Yes. And he'll be giving us a presentation on reconfigurable intelligence services for 6G. So, Luís,
Thank you, Nono. So I take this opportunity to thank the invitation to give this talk in this open day. So as you've seen, the title is quite.
just a second, I think it's on.
Okay, so as you've seen, the title is Reconfigurable and Large Surfaces. So this seems to be something really advanced and novel. So we'll try to understand what we are talking about here in the coming slides. In terms of the evolution of the different generations of mobile communications, we have seen more or less each 10 years a great jump in terms of technologies. Since the first generation of mobile communications in 1980. So more or less every 10 years we have a new generation, and so we are already expecting towards the end of this current decade the sixth generation. While right now we are already seeing a big increase of the 5G, of the fifth generation. You think I can take off the mask?
Yes.
Thank you, because speaking with the mask becomes more difficult. So we're seeing a big increase in terms of the deployment and the traffic that is already going in the current networks of 5G. So 5G will become mainstream in less than 5 years probably. But in the meanwhile, the scientific community is already focused on developing the new features that will characterize the sixth generation. One of them is going towards higher frequencies, towards the terahertz, or at least to the sub-terahertz, let's say, to the hundreds of gigahertz, to accumulate larger bandwidths. Okay, so larger bandwidth is more or less to enable these very large data rates, for example, 100 gigabits per second, up to 1 terabit per second in the downlink, which is quite significant. And to accommodate this with some spectral efficiency, you need a few tens of gigahertz of bandwidth, and it's very difficult to have that below the 100 gigahertz range. So this is the reason why the community is trying to investigate solutions for this. Okay, so maybe moving on. So the 6G in key performance indicators. So the 6G Flagship is an initiative from the University of Oulu, and they have more or less identified a few of the key points. For example, in terms of a specific feature that is expected is on the positioning, so the capability to accurately localize where are the terminals of the network, and even more things than that, to sense the environment and the people that are in this environment. To be more energy efficiency, so this is a great point of concern and of research. And other points, so reliability, density of terminals. So this one is very much connected with what we are going to talk about today, because to have a great density of devices, you need antennas, and antennas which have high gains in order to avoid interference. Okay. So antenna arrays. What are antenna arrays? and these surfaces that I had in the title are basically antenna arrays. They are not anything else than that. Okay, and as I was saying, the question of the user density, the antenna array, if you compare a traditional antenna where you have a broad beam, you address all of these devices at once, while with an antenna array and the usage of signal processing, in this case called techniques like massive MIMO, you are able to address all of these devices individually, and the larger is your array, as you can see here, the more devices you are able to address independently at the same time. Okay? And then these other points, such as positioning and sensing, they also come into play because we are not only talking about having communications, but also having sensing capability. And you will see this in this presentation. I'll show you some examples. Obviously, the high data rates are the obvious point because that's one of the main drivers for this research. So how does an antenna array work? So we typically think of an antenna array as some device with an input or output port because it can transmit and receive. And we think of using phase shifters and antenna elements, and by some magic we are able to steer the beam to a certain direction of interest. But basically in this animation you can understand better how it works, because by having these multiple antennas here with a specific phase shift, which is this angle phi here, and you can see that in time they are coming with a certain delay. The wave is departing from the antenna with a certain delay between antennas, and you can see in this case that this delay is such that the wave front is pointing towards this direction theta. Okay, so obviously what would happen if you had all of the same, if all of the phase shifters would have the same phase, basically the wave front would be in this front direction, so the phases would align at the antenna point, and so they would leave the antenna in phase, and you would have a perfectly parallel wave front. But as you create phase shift between elements, you can steer it to whatever direction you want. Okay? So this is the basic concept. And so, and then we could go into the mathematics just to make it more interesting, because if you think of these antenna elements with a certain distance, and typically this distance is half of the wavelength, okay? But in the newer generations and the newer surfaces that we are talking about, we can even think of reducing this to lower than that. But basically, when the antenna, for example, thinking of a wave being received here with a certain angle of incidence, the difference so imagine this ray that is received here, this ray that is parallel to this one will be received in the second antenna with an additional phase delay or time of d cosine of theta. Okay, this is a simple trigonometrical relation here. And so basically, if you do the maths and you make the substitutions of f by c over lambda and then x over lambda, so this distance x is basically this d cosine of theta. And so if you substitute here x by d cosine of theta times n, because as you are growing the number of antennas, this is being multiplied n times, okay? You end up with this equation, and this is the basic equation for the field of an antenna array, okay? So this is a simple diagram for you to understand. If in this case, considering these phase shifters, where we are putting them with time, so 3 delta t, 2 delta t, and so on, so different time shifts. And then in this case, we have the wavefront in this direction. So if you receive a wavefront in another direction than the direction where the antenna is pointing to, these signals will come with delays which will not sum in phase, and you will not receive the signal. Okay, so the only way of you receiving this wavefront with this direction is, and that's why the antenna basically only receives or transmits in this direction, because that's when the signals will head in phase. There is one aspect which is you might have heard in the media or in the literature as well, which is analog and digital beamforming. And what's the difference? Okay, in the left one we have an analog beamforming. Basically, what you need is these phase shifters or delays in each of the antenna elements. You can neglect this. This is just amplification. And then you combine this in the analog domain, and you go to a signal, to ADC, so you convert it to the digital domain, and you go to the processor. When you have full digital beamforming, it becomes more complex because you will need an RF chain in each of the antenna elements. So you need an ADC in each of the antenna elements. Obviously, this is more expensive and more complex. But then after everything is in the digital domain, you can do all of this phase shifting digitally, okay? So, and this combination becomes all in the digital domain, and so typically this is called digital precoding and signal processing in general. You can have a great degree of freedom by doing it in the digital domain. This is an example of the concept of a digital beamforming system with MIMO. So basically you have this DSP where you have these digital phase shifts, okay, so everything here is digital, okay, and you have specific phase shifts. So in this case we have specific phase shifts in blue here, which will create this beam in this direction, and you have other phase shifts that you cannot see because they are behind the blue one. Other phase shifts or weights, you can talk about weights as well, complex weights, because they will have a certain phase and magnitude, which will create a beam towards another direction. So basically each of these sets of weights will be able to steer each of these beams independently, and we might have multiple streams. We might have if we have many antennas and many of these weights combinations, if we have, for example, 64 sets of this, we might have 64 streams. So we have, in that point, we will call it already massive MIMO. Okay, just drink a bit of water. So now moving on, I have here what's the difference between a direct and a reflect array. Okay, so in a direct array you will have your signal or your RF chain, your signal generator, let's say here together with the antenna, and you distribute this signal through some distribution network. It could be splitters, for example. You distribute it so that the signal reaches each antenna element, and you provide it with the phase that you want, and you have the radiated wave. This is more or less what we've seen in the other slide. What is a reflector array? It's something different. The antenna itself does not have signal generation capability. Okay, the antenna is here. The only thing that's possible to do in the antenna is to create a phase shift in the element. But in this case, this phase shift that you can see here is connected with the element size. So this is a fixed reflect array without reconfiguration capability, let's say. So in this case, this phase array, this reflect array will reflect the signal towards this direction always. You cannot change it. This is because each element will create a certain phase shift, but each element will have a different size in order to create this certain phase shift. The signal itself is coming from here, from the feed. Okay. So here I'm showing you the difference between a fixed and a reconfigurable array. Okay. So this fixed array that I was explaining in the previous slide if you notice, there is some strange pattern here. You can see. So basically, this is the result of each element having a slightly different size, physical size. So the elements are actually different in size. And this is what will create the waves to interfere and reflect in a certain direction. But it's fixed. We cannot control it. Okay? But this one here is a reconfigurable one. All of the elements will be the same. You look at them and they are exactly the same. But what you have here, so basically this one corresponds to this schematic here. What you have in each element, it's some way of controlling the reflection. And in here, they call it here control device, and this can be a pin die or a varactor or a MEMS. So there are different devices for doing this. But this is the concept of a reconfigurable reflector array. Okay? And now, in order to try to articulate what I've been talking about, so why would we want a reconfigurable reflector array? And now we have to think about the radio environments and the fact that traditional environments are static, and so basically we take the wireless environment as something static which you cannot control. So you have walls and you have people and you have things with metal and so on, so you have reflections. So basically this standard radio environment will create problems as the signal propagates. So this random behavior, this degradation of the received signal due to this behavior. You have uncontrolled interactions of the waves with the environment. And so what you can do is to optimize the endpoints, transmitter and receiver. Okay? In a smart environment, you have a new degree of freedom, which is the capability to jointly optimize not only the endpoints, but also the wireless environment. So think of these intelligent surfaces and these large surfaces that I had in the title of my talk. If you are able to put these in buildings, in the walls of the building, in the ceilings, and whatever you can imagine in your everyday life, then you will be able to have a control on the wireless environment. And as such, this can be done with these surfaces of many antenna elements where you can have this electronic control as shown in the previous slide. Okay, what are reconfigurable intelligent surfaces then? You already have seen it in the concept of a reflector array, okay? And this is a reconfigurable reflector array is some more or less, let's say, also a reconfigurable intelligent surface. In fact, if you go to the literature, there are a few different terms to refer to it. For one of them is smart reflector arrays, and so basically it's having these antenna elements with some electronic device where you can, through the control of this bias voltage, so you have, for example, this pin diode, pin or varactor or whatever. If you control this bias voltage, you basically change the phase of the wave that is reflected in this element. Okay. So we have here an example. So you have an excident wave, exponential of j to pi ft, and basically you can either have reflection or transmission. So this would be the concept of refraction. If the surface is only reflective, so like the reflector rays, you are talking about this, and specifically about this theta, which is the angle that the wave acquires as it is reflected in this element. Okay, but in fact, rays, if you search literature, are able to provide many different ways of interacting with the incident electromagnetic waves. So reflection and refraction are the two that I just mentioned in the previous slide, but you can have others, such as splitting, absorption. So absorption is interesting because you might want to absorb the electromagnetic radiation and you don't want it to go anywhere. In specific applications, it can be interesting. Focusing, if you want to focus all the energy in a device, or imagine that you want to focus in a specific device, you are able to do it. And other more advanced functions, okay? So thinking about these diodes and the capability of tuning these diodes with some bias voltage, for example. This picture might remind you of the reflector array that you've seen in some pictures in the previous slides, where you've seen there was some pattern, right? That was connected with physical size. In this case, the colors represent phase, and so this is more or less to tell you that each element will create a specific phase reflection. For example, by using a varactor diode, in this case, these are results from an antenna in the 5 GHz range. These are actually two different papers. One is a varactor and the other is a pin. I will explain shortly. But basically, by applying a certain voltage, you can create a specific phase in reflection to each of these elements. So you understand that you could achieve each of these colors just by playing with the voltage. Okay? And this is basically the reflection coefficient, which basically tells you that the wave is always reflected. Okay? That's simplifying it just that. But if you use a pin diode, which is a more simple element than a varactor, you will basically just put it on or off, nothing else. Okay? So you will have only two states, and then this, which is an ideal control, will become this, which is an approximate control. So you won't have such a fine-grained control of the beams that you generate. Anyway, this approach is very interesting and is already in commercial phase because it's so simple. So what are some advantages that we can discuss here? So as I told you, so the RIS simply modifies the incident signal using these many elements which can be low cost and almost passive. I wouldn't say completely passive, because if you have a diode and you put a voltage and it consumes a few milliamps, it will still spend some amount of energy, and if this scales to millions of antennas in large walls, you will spend something. Okay? And I myself, I'm interested in researching ways of completely avoiding that. Okay? Other important aspects are this cost and energy efficiency, because you don't have to have a specific source of RF in this surface. So as to say, you don't need to do any processing, decoding, encoding, retransmission, anything. You just reflect, you just have the diode, nothing else. And the same goes for amplification. So you don't have noise, because you don't have to convert between analog and digital domain, and mixers, filters, whatever. You avoid all of this, and it becomes a very simple concept. So now going into applications. This slide, I have a picture with several applications. For some reason it disappeared. Anyway, so one of the most obvious applications that you think is communications coverage extension. Okay, so think of a signal source. You have a certain destination here. These RIS devices in the walls might be able to pick up this radiation from this source and reflect it towards the destination. If you are able to control the reflection angle, you will be able to reach this destination. This, for example, can be useful. Imagine a scenario where you have these obstacles. So this source does not have line of sight to this destination, but you are using millimeter wave, and there's no way of having communication between these nodes. But the RIS might be able to create a solution here. So this is a picture from a paper from last year, from a field trial some researchers have done. I don't remember exactly. I think this was in China, but this is the paper. And so they have a source here 50 meters away from the RIS, and this is the close-up of the source. So the RIS is placed here, is reflecting towards this receiver antenna, and this is the difference between not having the RIS and having the RIS. So this is the spectrum of the you basically can create a boost in the received signal by having this intelligent reflection here. You probably cannot see very well the image, but this is more than 1,000 elements in this small array. So another, for example, you can think of applications where you want to deploy these RESs in, for example, UAVs. So this UAV with IR is basically stands for intelligent reflector. So that you don't have, for example, line of sight between the base station and the user equipment, but through the reflecting surface in this UAV you are able to do it. And so this is also, as you can see, for example, some recent papers are addressing these specific use cases in UAV communications. Another possible application is security. So, for example, thinking of this user equipment which you want to reach from this access point, you have an eavesdropper in the way. The eavesdropper would basically intercept the signal that is directed to the user, but with the RES we are able to create a smart reflection which will have the exact phase that will cancel this incident signal. So basically the end result is that the eavesdropper cannot receive the signal, but this other reflection towards the user is different, and you boost the signal in the user. Okay? Another very interesting application is in radar sensing, and specifically in this case you can use it in human sensing and possibly, for example, for posture recognition. And so this is the concept. So basically you have this human here, you have the RES device, you have the transmitter source, so you illuminate with RF waves all of this surface. The elements will be tuned in real time to create beams in covering every possible direction. So you can basically do like a leader sweep, like a radar sweep. You can sweep all of your scene, and by the reflections that will be captured in this receiver here, you can reconstruct an image. In this case, this is one example of a real image that was reconstructed from a device that was used in an experiment in 2019 in this paper. So you can see here what I was saying about the multiple beams, basically sweeping all of your scene, and then you gather these echoes with a certain protocol, and you are able to reconstruct this. So this one was done at 5 gigahertz, but as you increase in frequency, you are able to get this more and more refined. Okay. So one other idea of reconfigurable surfaces is going beyond RF and going to light. Okay. So LiFi is let's say an analog for Wi-Fi, which uses light instead of radio waves. Okay. And this LiFi is already a standardized communication solution that basically was invented by Harold Haas from the University of Edinburgh in Scotland, and he created this spin-off company, and he has been very successful so far, but basically it's communicating with light. But in this paper from last year, they have proposed that why not using this concept of reconfigurable intelligent surfaces also with light. Okay, so this concept of an optical metasurface with light manipulation possibilities has came up, and basically with light you can have more or less the same principles as you have with RF. Okay, for example, if you engineer your material to create a certain reflection, and it's anomalous, because if it wasn't anomalous, it would reflect according to Snell's law. Okay, but if you are able to engineer the surface, you will be able to control this reflection angle. Other things like this incident beam might have ordinary refraction, as you know from looking at a pen inside a glass with water, but you can also engineer it to obtain negative refraction and other things like amplification, attenuation, wavelength manipulation, etc. So how can a LiFi RIS be of any use? So basically they propose this for either beam steering. For example, imagine a light emitting diode in the ceiling like you have here, and you put the RIS in front of this light source. You can control basically like how you spread your light signal. For example, a larger field of view, giving a further coverage area with lower light intensity, or for example here a lower field of view helping to concentrate the beam in a specific user, or also the beam steering like we have in RF, okay, like beamforming. So you can beam steer the light towards this user to avoid that it loses the connection. Another aspect would be, for example, this dynamic angular diversity. If you have light sources with multiple sources, independent sources, this is one kind of solution that exists. But basically, if you want to modulate specific information to a target user using these sources, because they are uncontrolled, you will end up sending the signal that is directed to one to the other and so on. So you will have interference. But with these RISs, with the surfaces in front of these sources, you are able to manipulate each beam exactly to the intended user. Okay. So in this same paper, they basically thought about these possible application scenarios. For example, thinking of outdoor, for example, where you have the connection between these cars, for example, which could be occluded through these trees, but you have this smart reflection here, or you want to from this light post that you have on the street, you want to reflect smartly to this user, but not to this one, because this one would be an interfering user or a eavesdropper. Other possibilities exist. So, for example, the indoor scenario as well is covered here. So moving on towards the end of the presentation. So some promising directions that the 6G Flagship initiative has already thought about in both hardware and services, and just to make note that massive antenna arrays are already one of those here so in this graphic where you have low impact, high impact, low uncertainty, high uncertainty, massive antenna arrays are considered low uncertainty and high impact. Okay. And these could also take advantage of some other things. For example, visible light communications that we were talking about are also here. And then these are more technological aspects, such as terahertz, like going to higher frequencies, CMOS, like the fabrication techniques with CMOS to make this more accessible in terms of fabrication. Graphene, which could be a material that would enable these massive antenna arrays to work at these higher frequencies. But as you can see, this is already in the high uncertainty kind of range. Specific materials as well. And then this is more about services that can be obtained. For example, the positioning is one of the services that I talked about. The radio sensing and imaging as well. And for example, other things like wearables and mixed reality. These are also these are all a sort of services that can be very interesting and are basically making this way towards the 6G. So in terms of research directions for antenna arrays, so one of them is this extremely large aperture array. So where we can start thinking about antenna arrays, for example, that could cover an entire facade of a building. Okay. Okay, so this would be really a huge thing, but you could use something clever like having just one antenna element per window, things like that. But when you look at the whole of this aperture, it's a basically massive array with an incredible aperture of many meters, where you are able to basically focus completely the energy in a specific terminal device. And so with this, you could pack many more devices in terms of user density than what you can with a traditional antenna array, which is represented by this small antenna array here, where it's basically targeting the beam towards this user. So by using this extreme aperture, you go from this concept, which is based on far field, to this concept, which is based on the near field. So the user will always be in the near field of the antenna, and you are able to create this beam focusing, which is something very interesting. The other one is the holographic massive MIMO, which basically instead of having antennas that are separated like here, you try to pack as many antennas as you can into a limited surface area, so as to make an almost continuous antenna surface. Okay? And this could be implemented in two different ways, either as a RIS. So here you can immediately see this is exactly what we were discussing until now, the RIS, where you reflect intelligently to the incident signal, or as an active transmitter or active array, where you have your signal source together with your array, and then you have this smart surface. Okay, there are also researchers already thinking of combining these two things. Okay, having active array with also smart reflection capabilities. Okay, so this is also an hybrid combination, which is very interesting, and I myself am also interested in exploring that possibility in my future roadmap of research. And then machine learning, which nowadays is a hype in many science fields, and it couldn't also pass here without mentioning that machine learning is also a very useful tool and capability that you can take advantage to optimize these antennas, and when you want, for example, to have these many elements in these antennas, you need to control all of these elements to create these beams, and it's a difficult problem to solve in terms of simulation and so on. So by integrating machine learning, you can better optimize these problems and achieve better results. Another promising technique that can also be related with this smart surfaces and so on is that you could have in these smart surfaces some computing, and you could also have some artificial intelligence being placed there. So we can call this the extreme edge. So instead of having a centralized solution in the cloud, you start moving towards the edge, and then to the extreme edge, where you basically extreme here basically means that it's fast, low power, safe, autonomous. So basically that's the idea, and that you have to understand that you will need to have some analog functionality, because it will be very efficient compared to digital functionality, and you can take advantage of that to do some processing at this extreme edge, and these surfaces could be a way of doing this processing. Okay, and it could even be distributed. And last but not the least, the electricity demand is a problem that is growing, and this is a prediction up to 2030. And for example, you can see that it's expected that, for example, although consumer devices, that is this one, are getting more efficient and they are probably reducing slightly, For example, the fixed access use of the network is spending more and more energy, and also fixed access with wireless use and wireless networks, data centers. Data centers are getting really a huge part of this. So this means that all of the scientific community has to make an effort in trying to make this not so spike in the coming years, because if this is like this in just less than 10 years, I don't know how it will be in for example, in 2050 or so on. So to finalize the presentation, I have just a quick overview of some capabilities we have within our Center for Telecommunications and Multimedia at INESTEC. And so I was talking about antenna arrays and antenna design, and this is not by coincidence, because this is because we have an active area of research in this topic. And so we are doing design of planar antennas and antenna arrays up to 300 gigahertz. So we have actually published last year the first paper on a 300 gigahertz antenna. Also, the waveguide transitions, like this one that you can see here, where you need to transit the signal from a planar device like an antenna or a PCB to a waveguide. The capability for doing the 3D electromagnetic simulation, as you can see in these screenshots. So this is very important to accurately predict the antenna performance. Characterization in anechoic chamber, so this is the chamber that we have available to characterize our antennas here in FILP. And you will see a new one that we have, which is targeting higher frequencies. So this one is going up to 40 gigahertz, but we have an even newer one that goes even higher. And some of the targeted applications that they were already mentioned during today's presentation. So we have another area on the electronics design where we are focused on, for example, on the design of integrated circuits, and we have also the capability, and many times we fabricate these circuits at Aeropractice facilities through IMEC in Belgium. And so it's not only design, but we get to the point of getting these devices fabricated and receiving them, and we wire bond them, so we have wire bonding machine. We are able to actually characterize and make experimental measurements. Another very promising area which we are currently working is on thin film transistors and memristors. For example, here in this picture you can see a circuit that was deposited here on this thin film substrate. So this is basically a substrate where you can only manufacture things here if the temperature is not very high, otherwise it wouldn't work and you would destroy it. And so with some specific manufacturing techniques that work only below 150 degrees, we are able to deposit these devices. Specifically, memristors is one of the devices that we are working with to try to create neural networks that can support, for example, these so-called neuromorphic computing concepts, where the idea is to have very low power computation in support of the extreme edge that I was talking just a few minutes before. Another area of research which has significant capability in our center is the reconfigurable computing. So here we are talking about basically FPGAs, so these field programmable gate arrays, but not only. So one of the things we are developing is, for example, digital beamforming algorithms. So the pin diodes that I was showing you, and I was telling you that you can control those with voltages, basically you will need one of these FPGAs to control and to cleverly create all of these beams in these antennas. So this is something that then we can take advantage of this capability in the hardware domain to make this whole system work. And other areas of activity include high-level synthesis, C, C++, OpenCL, and tools and compilers for parallel compute architectures like custom-grained reconfigurable arrays. And to finalize, so this is my last slide. So this is an overview of our communications laboratory in STEC building. And this is the chamber that I was telling you about a few moments ago, the new chamber that we have built that goes up to 115 gigahertz using these special frequency extenders. And this is our bonding machine that we can use to wire bond the integrated circuits. And I actually did not update this picture. The lab has been fully renovated, so if you have the opportunity to visit us, you will see we have a completely new laboratory now with many improved features. And so I hope if you are interested in making research in cooperation with us, just contact me and I will be happy to talk with you and further take this on. Thank you.
So we still have a little bit of time, so if there's a question or two, we can still take it if you like.
I noticed that the applications through of LiFi with RFS were like using only artificial light. Are there any applications towards natural light?
Well, with natural light, what's being done, and I'm also more or less trying to follow this, is basically energy harvesting, like with solar cells. So the natural light that you can have, and even with artificial light, you can take advantage of it to harvest energy and think about IoT nodes that could be completely batteryless and just having, for example, supercapacitors, and thinking about this move towards fully printed electronics devices and very low cost, like these thin films that I was showing now. So other than that, I haven't, and as you've seen, this concept of the RIS in the optical domain is really recent. So this paper has like less than 6 months. So this is all emerging now. So probably if we were here in 10 years time, in 2032, probably many things will happen until then, but right now this is some initial ideas in this field.
Okay. I think I have a question. Do you think that when we're talking about power harvesting with radio frequency, right, that antenna arrays could be applied to do directed power harvesting without
Yes.
waste of
Yes.
power?
So I was talking about harvesting from light, but harvesting from RF is also something that if you search the literature, there are many groups already working on this, and also using the RIS for that. Okay,
Right.
so using that, and they call it SWIFT, so simultaneous simultaneous information and wireless power. So basically you combine information transfer with power, and the fact that the RIS can focus the beam towards a device can be very useful to, for example, now I will charge that IoT node which is running our battery, and it doesn't have light absorption lights or solar panels or anything, and it just has an antenna, and so so it's also very interesting for that.
But I was thinking for the drones that fly indefinitely by being charged from base stations.
Yeah, so
Transmission.
yes, that's also something that has been approached in the literature, and also even further than that, like trying to transmit energy to satellites and things like that.
Okay. All right, so thank you, Luis. I think we're just
Okay.
actually let's thank Luis again. The answers, and we're just on time. And the two following workshops are both at INASP, Auditorium A and B. One of them actually on antenna arrays, and another one is a repeat from yesterday from the MCT group on creative music. So I hope to see some of you there as well. And thank you, Luis. Thank you everyone for being here.